Okay, good. So good morning again. Welcome back to Big Data. So last week we finished up with Spark and MapReduce and that distributed processing aspect of the course. There are some more morsels on distributed processing later on, like next week or the week after, when we will be discussing decentralized NoSQL data stores. But for today, and this week and probably next week too, we will be looking at distributed NoSQL data stores, specifically key value stores, not because they are more important or whatever, but because they are probably the simpler to understand, the simplest to understand, and also other key value stores, other NoSQL data stores like graph databases and document stores and so on, are practically modeled on top of a key value store. So the key value store, or at least this type of key value store that we will see, are the basis of a number of other NoSQL data stores. Today we will do quite a bit of brainstorming. Okay. So I guess you've done your pre-session reading. What I would suggest you do then is, keep the pre-session reading in mind, but for the first part of today's lecture, try not to be affected by it, because what I will have you do is I will have you work in teams to come up with at least some aspects of a design. And I don't want you to come up with like the big table design. I want to come up with what you think is the right thing to do. Okay. So let's say you are an SRE, you're an engineer or a designer or whatever at a big company. A big company that has lots of customers, lots of transactions, lots of projects, lots of interactions, and in general, a lot of data. Okay. And then your line manager or your client comes to you and asks you to design the company's new database to store and handle everything. Asking how I know, typically what happens is that your client either has very vague requirements, like I want to store this data and I want to be able to query it fast, or has very specific requirements, as in I want to be able to get to this data in like 200 milliseconds or better. In any case, they come and say, I want you to design a data store that can store and handle everything. And you say, what do you mean everything? And they say, everything. Okay. Let's try to crack this nut. So let's start thinking, well, what are your functional requirements? That's the part of the requirements capturing where you just talk to your client and try to understand what is it that they need, not necessarily what is it that they want. Yeah. So what are your functional requirements? What do you expect the API of this data store to be? Like, how do you expect to access it? Did you just plan to do like single item insertions and deletions and queries? Do you want to have multi-item access? Do you want to have transactions? And your queries, will they be point queries? Will they be range queries? Will they be something else? What are the functional requirements? And then what are your non-functional requirements? And non-functional requirements are characteristics of the system that are not defined by its functionality, but by properties that the system exhibits. So for example, a non-functional requirement could be that I want the system to be scalable, or to be fault tolerant, or to be, you name it. Okay. So what are typical functional requirements for a store like this? You want it to support, the basic operations, CRUD. So you want it to be able to create, read, update, and delete items. Okay, but what are the semantics here? And so when you create an item, do you expect when you create an item and then you create something with the same ID, for example, do you expect that to be an error, or do you expect that to be a new version of the old item, or to just override the old item? If you delete an item, do you expect it to go away or to just subside as an old version, and so on? Do you have a schema? These are NoSQL data stores we're talking about here. But at this stage, you're talking to your client. You don't yet know what is it that they need, right? So what does your data look like? Is there some pre-specified schema where you know that every item needs to have all of these properties or attributes? Or is it, is the schema flexible, or is there no schema at all? Do you plan to have transactions? And by transactions, I mean the ability of the system to support pretty much ACID, some level of isolation. And what are the access patterns? So how exactly do you plan to access the data? What is the algorithms you will be running on this data store? Is it just single item input output, like a hash table, or is it something more convoluted? I mean, if you want to do range queries over a range of keys, then all of a sudden the hash table interface is not good enough. If you want to do something more convoluted than that, for example, for graph databases, for example, we need to come up with more bespoke data structures. And finally, the applications that will be running on this data store, are they homogeneous or heterogeneous? Do we need to discuss the things we just said, like schema, transactions, access pattern, semantics? Do we need to discuss them for every single application because they are all different? Or would one design one of these sets of requirements fit every application? Semantics, someone asked what semantics are here. These are the semantics of these operations. So when you create something, it's not always obvious what that means. It could mean that you just add something new to your data store. But if something exists already, what should the create do? Should it override the previous version? Or what was already in there? Should it create a new version? Should it error out and say, I can't do it, this key already exists, and so on, right? Same for delete. I mean, if you delete something, it could be the case that you need to physically go where that thing is stored and zero out the space. Or it could be that delete just marks that thing as deleted, but leaves it in place. Or it could be that you add a new version that says whatever was there has now been deleted, and so on. Okay, that's the semantics aspect. And now the non-functional requirements, right? Typically, what you would get in these situations is that your clients would want high throughput and low latency writes, high throughput and low latency reads. They want the system to be scalable. They want the system to be fault tolerant, and they want the system to be highly available. Now, typically, you would try and understand exactly what they mean by this. So high throughput, what does that mean for you? Someone used to, using systems that are, for example, high performance in memory databases, they would expect throughputs and latencies to be through the roof. Someone who's using, more, let's say, down-to-earth distributed databases, they would still expect high throughput and low latency, but not at the same level as the first person, and so on. Okay, so here let's think that, let's put ourselves in this situation, right? Where at this big data corporation, let's assume that this is a place where we're already using Hadoop. It's SDFS and possibly MapReduce or Spark. Okay, so when we're talking about high throughput and low latency, that's in that context, right? So high throughput as in how high of a throughput can you sustain on a cluster that runs something like SDFS, right? And scalability, we're talking, that kind of scale. So hundreds to thousands of computers, but no more than that. Fault tolerance, we've said in the past that every single data center will at any point in time have at least one fault. So we should be able to work around that. And we want it to be highly available. Okay. And this is highly available in the face of network partitions. So as you may remember from the past, when we were discussing the CAP theorem, what we want to go for here is an AEP system, okay? A system that offers availability in the face of partitions, but not necessarily, high level of consistency. Or maybe that's something we can discuss, right? That's something we can discuss. So, okay, right? And we want everything. We want everything. So, if we were indeed in that situation, we would sit back and say, okay, what you ask for there, you can do it with a centralized relational database. At least the functional requirements can be addressed by just a run-of-the-mill relational database. What's wrong with that, right? Or if you don't want a centralized database because, for example, your data is too large, too big, why not use a distributed relational database? There's several good offerings out there. Legend has it that Facebook to this day is using a cluster of MySQL databases to store a big chunk of their data. So what's wrong with that? Yeah. And if distributed relational databases are not a good option, why not go in federated, right? Where you have different types of databases connected in this, heterogeneous but still federated system. So what's wrong with all of this? Yeah. And if that's not enough, if you've managed to shoot down all of these, what is wrong with distributed file systems like HDFS? So let's try and go through these one at a time. Okay. What's wrong with the centralized relational databases? We sort of alluded to that in the very first lecture. So relational databases come with a set of design decisions that hurt performance when you go at this big of a scale. Relational databases are designed to offer, they are pretty much CA systems, right? High consistency, highly consistent, and highly available. But if something goes wrong, they cannot sustain any. They don't really do partitions. They don't do partitions because this is a centralized scenario. But in a distributed scenario, you would also be looking at probably a CA or a CP system. So our client said that high availability is one of their requirements. Okay, so none of these. Where's my mouse thing? There you go. So centralized or distributed or federated relational databases are not really good at that because they are designed to offer consistency. Okay, and in a distributed system like this, we know that consistency and availability are not really good friends. So let's put this on the side, all of the relational offerings on the side, and look at something like a distributed file system, like HDFS. We've said in the past that HDFS is highly available, is fault tolerant. It ticks a lot of the boxes, but not all of the boxes, right? So you can create, read, update, delete stuff on HDFS. But we've seen in the past that HDFS, for example, needs or is happier with big files, like the block size is big. So if you were thinking of having, let's say, one file for every item you store in HDFS, that's a big no-no. So you need to sort of cram many items in these big blocks that HDFS is happy with, but then you're back at square zero. So how do you organize these items in these big blocks? How do you access them? How do you index them, and so on? So if you remember what we were talking about in the database systems course or IDSS, the first lecture was actually looking at how do you organize things in a block, right? And here you have these big blocks, so you can actually fit many of these things in there. So organization becomes even more important. The other thing that's wrong with HDFS is, as we've said in the past, it's really good as a high throughput data sink, not so good as a low latency source of information. Definitely not good for random accesses. So HDFS won't cut it either, right? So we need something else. We can't use any of these things. So before we move on, just some glossary here for people who may not have seen this in the past. Acid and base. So acid, I hope you've seen it. I think we discussed this in the database or IDSS courses. Acid is a set of properties offered typically by relational databases. So atomicity, consistency, isolation, durability. We've discussed this again in the past. Base, I think we've also discussed it in the past, right? I think it was the very first lecture, by the way. These two are sort of opposite sides of the story, like the opposite ends of a spectrum. In an acid system, typically you strive for atomicity, isolation, and durability. You want all of the concurrent transactions to appear as if they're atomic, so that they all of their operations happen at just one point in time. You want them to be isolated from each other, so you don't want a transaction that runs and does stuff to see what another transaction does, another concurrent transaction does, unless that other transaction has committed. You want all of the data to be stored durably, and unless it's durably stored, the transaction is not complete. And you want the data to be, you want the database to always be at a consistent state. So even in a centralized system, if you have something like integrity constraints, these must be met at all points in time. Otherwise, your transaction needs to be aborted. Okay. Now, when we move to a distributed system, if we still want to support acid semantics, we either need to, let's say, we need to twist the story a bit. We can't really do properly acid semantics when we want high availability and when we don't impose any structure on the data. So if for example, we could say we take the data and we split it in pieces, and within every piece we can have acid, but across pieces we need more mechanisms in place. That's something that may happen. It actually does happen in several systems out there. The problem with ACID is the same problem that relational databases have, right? That's the source of the problem. All of these focus on consistency and atomicity and isolation. That hurts performance. So this wave of NoSQL data stores that was they were quite popular, and they've probably sort of dominate this space over the past couple of decades. They went with something called base semantics. So base stands for basically available, soft state, and eventually consistent. What does this mean? It means that your system is basically available, as in it will be able to answer queries at any point in time, but what you get back may not necessarily be the latest version of whatever you're going for, or may not be the same across all copies of that thing on your distributed system. Soft state stands for, it's supposed to denote the fact that you don't really have like proper logs here. You have leashes. Or leases, I should say. Leases is something that was mentioned back when we were discussing HDFS. So what is a lease, right? And how does it differ from a log? When you acquire a log, you hold the log for as long as you are around. You know, if something happens to you, if you have a process that holds a log and the process dies, then there need to be some mechanism in place to detect that the process died and to release the log. And even then, it's not actually clear what happened or what should be the next step. If you haven't heard of this terminology, typically these logs are called poisoned. So you have a log that has been logged by some process that died. So what do we do? Do I just unlock it? But what if that process also held other logs, and these are there's some semantics behind the order in which these logs should be unlocked, right? So for me now, this log is poison, right? We can't really have that in a distributed system like this. So what we do is soft state. Soft state means I acquire let's call it a log. Actually, the term used is a lease. I acquire this lease that is like a log, but it also has a timeout attached to it. And every now and then, I need to renew the lease, right? So I acquire this lease on an item. I'm doing my work. Every now and then, I need to go to wherever I acquired the lease from and say, renew the lease. And then, sometime later, renew the lease until I no longer need it. And then I can unlock it or release the lease. Why is this important? Because now I have a built-in mechanism to detect failures, right? If a process dies or something goes wrong, that process will not renew the lease, so the lease will expire, and whatever was locked by the lease will now be unlocked. Okay. And then eventually consistent means that my system does not offer strong consistency in the same sense as an ACID system, but and what this means is that if I have many transactions, many things that change the data, and this data is replicated across the system, these different replicas for the same item might actually have different values at different points in time, and these different values will also be visible to the user, possibly. I'll give you an example here. So say I have an item that is copied 3 times. I have three copies of an item. And I have a client that wants to update the value of this item, right? So what does the client need to do? It needs to send the update to the first replica, to the second replica, to the third replica, somehow, But if there is a second client that tries to read the value of that replica, that client, depending on which replica they asked and which replica I've updated so far, they might see the old or the new version, okay? The old or the new value. In a strongly consistent system, I would run a different kind of protocol. So I would send these values to the replicas, but I would tell them, don't give this back to the client just yet until I tell you so. So I would send these values to all of them. And once all of them had the new value, I would then go back and tell them, now it's okay to give the new value to the client. Okay. Roughly speaking, because there are more steps to these protocols. But Base doesn't do any of that. But Base says you send your data to the replicas, and these replicas may be inconsistent and may reply with inconsistent data to the clients. But if you leave the system alone long enough, then all of these will eventually have the same data. All of these will be eventually consistent. So someone asks, how is giving an older version of the data a good option? Wouldn't the client be misled? If you're referring to what happens in the strongly consistent case, I think that's what the question is about. The whole point is that you want all of your clients to see the same data at any point in time. if you have sent new data and the new data is not visible yet, then for the client that makes no difference. The client doesn't know that some new data points have been added to your data. Some new information is there. In database language, this is what we would call the point of serialization. So you have these transactions that run concurrently, a transaction that updates the items and a transaction that reads the items. And going by atomicity and isolation and so on, what you want the result to be is the same as if these transactions were running sequentially, one after the other. So the question is, which one is the first and which one is the second? So at some point you serialize them. You decide that the write transaction goes first, the read transaction goes second, or the read transaction goes first, the write transaction goes second. Okay. But again, what does this mean? This is an oversimplification. What it means is that if you decide that the read transaction goes first, write transaction goes second, the read transaction will see the old value of the data. If you decide the other way around, then the read transaction should see the new value of the data. Okay, so it's not about misleading; it's about semantics in this case. In Bayes, you don't really offer this strong level of semantics, or that can be a long discussion. We will actually touch upon this subject multiple times in the coming weeks. Okay. So, I mean, there is an internal joke here about acid and base, and that joke is that you may remember pH from your secondary school years. So pH, that's chemistry, right? It measures the power of hydrogen atoms in a solution. Okay. And the lower pH is, the more acidic your solution is. And that means, no, pH is not examinable. This is just an internal joke here. But when your solution is more acidic, the atoms in it are supposed to be moving more, like they're in constant motion. Okay, and this means that in an acid system, what's the joke behind this, right? In an acid system, because of the constant motion, you need to do more checks. Okay, if pH is higher, then you have a more basic or alkaline solution, lower motion of your hydrogen atoms, and so you can relax your constraints. Okay, that's it's not example, it's just an example, just an internal joke here. Okay, and then keep in mind Brewer's gap theorem. We've seen this in the past. We have consistency, availability, and partition tolerance. You can only have two of these at any point in time. Good. Okay. So that's all very interesting and possibly funny. But what does this all mean for the system and the application? And when does each of these make sense? Okay. So for the system, being base as opposed to acid means that, as we said earlier, there are fewer checks to be run, fewer guarantees to be upheld. So the system doesn't need to be as rigid as in an acid case. You don't need to have, you don't necessarily need to have a lock manager, for example, to coordinate locking, unlocking, detect deadlocks, and so on. You don't need to walk through your, you don't necessarily need a concurrency control mechanism here, like you would in a typical database, in a relational database, where you would be acquiring logs at specific warning times, or you would be verifying that no conflict happened before you commit, and so on. So the system is now much simpler to design and implement. Okay. But this is a zero-sum game. Okay. So what this means is that this complexity now to some extent passes on to the application. So if you are using a system like this, like a base system, and you need strong semantics, then it's the application that needs to have the extra logic to guarantee that those semantics are there. Okay, that's the big catch. But at the same time, it's not as big as it is, because the applications that typically would run on a NoSQL data store would not need that level of consistency. So, a typical example here of where such a database, such a data store would be used is something like an online messaging system. Think, I don't know, of Facebook Messenger, right? Or an online like basket when you're shopping, like, think of Amazon basket. Okay. So what happens here? Let's think about the messaging case. You're talking to a friend of yours, and actually you have multiple friends talking in the same channel. Okay. You type a message, the message goes off to your friends. It might appear on the screen of some of your friends before it appears on the screen of some other friends. And if everybody's talking at the same time, those messages might be somewhat out of order across your friends' screens, okay, and your screen, of course. But is that the end of the world? Actually, no. For an application like this, it doesn't really make a big difference. Let's think of the online basket example. So you go through Amazon or whatever, some online shopping service, and you find an item that you like, you add it to the basket, okay? And then you find another item that you like and you add it to the basket. And then at some point you click on your basket to see what's already in there. Is it that big of a concern if the items were added to your basket in a different order? Or is it that big of a concern if, let's see, if you refresh the screen, and every time you refresh the screen, you see those items changing order? It's not the end of the world. Actually, these are things that you could actually handle in the application. But regardless, from the data systems point of view, it doesn't really make a big difference, right? So when does each of these make sense? It all boils down to what are your functional requirements and the semantics you want. Okay, if you want strong consistency semantics, of course, a NoSQL data store, or actually I should say a data store offering base semantics is not the best option, probably, right? Unless what you would need on top of base is not that much and it can be easily implemented in the application. But if what you care for is the ability to add things to your data store at a high rate, you really need high throughput, and you don't really care so much about consistency and so on, then there's nothing that could probably beat a NoSQL data store, a base data store. And that's actually how these things came to be, right? So you had the likes of Google and Facebook and Amazon and so on. And these guys have so many clients, so many changes, so many data items added to their system at any point in time. And they saw that when they were using a relational database, distributed or otherwise, they were hitting the throughput limits of the system. They were getting up to some throughput. They couldn't get any more than that unless they considerably scaled up their nodes, and that was not economical. Okay, so they took a step back and thought, okay, what are the semantics I need? I don't really need all of this strong consistency, right? Maybe I can relax some things here, and by the time you start relaxing things, the system becomes simpler, and a simpler system is quite often also faster. Okay. One or two more things for glossary, and then we move on to the proper brainstorming. So let's say you have a data collection, and conceptually, you have records or rows. You have an identifier for each of these, a key that uniquely identifies each of these records, each of these rows, and then each record has a number of columns. Okay, so here for simplicity, all records have the same number of columns, and all columns have some value. That's not a requirement in the NoSQL world, but bear with me. Okay, so let's say this is your collection, 3 records with a key and 3 attributes each. Now you need to take this and store it. And when you store it, like on disk or in main memory, you are implicitly serialized. No, I mean, you are implicitly, what's the term? Projecting this 2D space onto a 1D space. Okay, so I mean, think of the memory. The memory is just this long array where you have just cells of memory, and every cell is identified by its address. Well, that's one model. Disk similarly, right? So disk is just conceptually this long array of blocks or locations on disk identified by the location. So you need to take this collection and project it onto this 1D space. Okay, and how do you do it? Well, there are many ways to do it. 2 of the main ones, and this simplification here is row major or column major. So first by row or first by column. If you do it first by row, this is what we call a row store. And in a row store, and we will see how things are stored. If it's done in column major format or first by column, this is what we call a column store. Okay. So in a row store, you take these values one row after another, and you store them like this. So you would have all of the properties, like the key and the attribute values for the first row stored like this. Then all of the values of the second row, then all of the values for the third row, and so on. In the column store, you would go column first. So you would go first all of the data of the first row, of the first column, excuse me, then all the data of the second column. So 1, 2, 3, ABC capital, alpha, beta, gamma, and then whatever. Okay. And when is each of these the best option? It all boils down to what are your access patterns. So how do you access your data? What are the kind of queries you want to address? Typically, systems that are transactional systems, or operational as they're called, like OLTP databases. Most of the databases you may have seen that have the relational tag on them. They are row stores. And typically in these cases, you want to be able to insert a record very quickly. And when you query something, when you query your database, you probably look for complete records, or for a large percentage, percentage of the attributes of the record. So it's easier to say, let me find where that record begins here. It begins here. Yeah. And then reading the data of that record is just a sequential read on my disk. I'll just read, or on the memory. Okay, I'll just read one after the other, the items. But if you do something like analytics queries, so this is your typical OLAP situation, you would probably want to look at only a small subset of these attributes at a time. So for example, you want to say, if this is my my clients, I want to find, for example, what is the average amount of money my client spent. So that would be that query would be just a Apologies, network went down. Here we go. Is the recording still on? Yes, recording still on. Good. So in this case, then, let's get this out of the way. Computing the average amount of money your clients have spent, if that's what this table is all about, would be a matter of just looking at only this column and computing the average of the values in it. Okay. And then in this case, what you want to do, if you still had a row store, you would need to navigate to the record where the first record begins, skip to where the value is for how much that guy has spent, then skip to where the value is for the second record, skip to where the value is for the third record, and so on. And you're essentially do just random IO to get each one of these attributes. Okay. Whereas if you have a column store, what you need to do is find where that column begins here, and then just read sequentially through it. It's much more efficient to do it like this. So someone asks, how does group by on multiple columns work in column store? Is that still the best store for the scenario? Okay. So there are several nuances to how column stores work that we cannot really get into in the context of just this one lecture. But if you think about it, typically there is some inherent ordering in how things are stored in your tables, in your database. And quite often it is the case that you have, for example, repeating values, right? Think of a database of all people in the UK, where you have a column that says what city do they live in, okay? And then you have another column that says what year they were born in. So one could, let's say, rearrange the rows or insert them in such a way that you have a long sequence of people, all of which live in Glasgow. Okay, a column store would typically compress that. So it typically would say Glasgow, and then Glasgow appears for that many columns. And what you would store here would be, Glasgow and the number of the rows where it appears. So there are tricks done in column stores to lower the number of items you store. And in that sense, you are also increasing, your read throughput, you're increasing your processing throughput, and so on. Where column stores really flop is actually the answer to the question that was just asked. So doesn't reading writing in row or column differ only by offsets in storage? And then we won't have increasing complexity. So if what you want to do is offer those strong semantics, if you want to say that someone will change something in this row, and I want that change to be atomically visible. So either all of the change is visible or none of the change is visible. Okay, it's much simpler to do it in a row store than it is to do in a column store. Okay. Also with locking. So if you wanted to be able to lock things here, you would typically lock rows, for transaction processing. It's much simpler to say that I have a lock that captures or that locks or protects these guys here, and then another lock that protects these guys here, than it is to say I have a lock that protects this guy and that random guy and that random guy and that random guy. Okay. So that's where, that's typically how you would decide between the two. Am I doing more operational work? So lots of insertions, deletions all the time. And what I care for is isolation and atomicity and so on. Or am I doing more analytics? So is my data set practically read-only or very slowly changing? But what I really want is high performance in my analytics. Do we not? So there's a question here that says, do we not log based on processes? Why log based on what is accessed? See, that's what I was saying. We can't really get into all of this detail in just this one lecture. So what we never managed to cover in database systems or IDSS is how do you actually do transactional processing, okay? And how do you guarantee this atomicity and isolation and so on? The way you do it, I mean, how much time do we have? Let's take this on the forum or offline if you want. I mean, this is quite very close to my heart. Yes, I can provide some further reading. That's a good suggestion. Okay, good. So with that said, then we now sort of have a mental model in our mind. Okay, so we want a highly available system. That means transactions are probably not that important. Maybe single row transactions, but definitely not multi-row transactions. We want it, as I said, to be highly available. We want it to be scalable. So we're probably looking at something like maybe like a column store, but with some row store properties, or maybe like a row store, but with some column store properties. We can't really decide between the two. We know we don't need the proper relational database. We don't need all of that overhead and all of that consistency and so on. But we want it to be scalable. We are expecting a very high volume of data being added, and we expect a very high probably volume of queries coming. So we need to scale this. I don't think we would be able to do it on just the one machine. Okay. So how do we scale this? Remember, you can scale something up or you can scale something out. If you scale something up, you just add more resources with more hardware. You have a server that has that much RAM. It's not enough. You go and add more RAM. Not enough, more RAM. It has X cores, and you need more than that. You go and add more cores. How do you add more cores? Well, you might have empty sockets. You add more CPUs. You need more than that. You need to throw the motherboard out, get another one with more sockets, or get a CPU with more cores, and go from there. So scaling up is not necessarily easy, and it's definitely not cheap. How do you scale out then? Scaling out means I add more machines to my distributed system. And if these machines are what we call commodity machines, then it's a much more economical way of adding cores and RAM and disks and so on to your system than it is to scaling it up. How do we scale something up though, right? That's that's a question we've answered at least thrice so far, at least 3 times, okay? How do we scale something up? Well, we partition it and then we replicate it. So we partition it so that we have a unit of replication, and then that's the unit that we copy around, okay? And this partitioning and replication gives us the throughput we want. It gives us the fault tolerance we want and the availability we want, and so on. But so far, when we were looking at HDFS, partitioning was fairly simple. We had this big file and we said, okay, we'll chop it in pieces one after the other, and then that's how we partition it. But here we have an option. We can actually choose exactly how we partition the conceptual, the data model first, and then apply that partitioning on a physical level. So think of that table we had earlier here. Okay, this guy. We can partition it horizontally or vertically, or maybe something else. Okay, what does horizontally mean? It means that I will do horizontal cuts. Okay, I will say I will cut it here, and then these first 2 rows are one partition, and whatever comes after that is another partition. Okay, that's horizontal partitioning. There is vertical partitioning that says I'll cut down here, right, like this. So Column 1 is one partition, column 2 and column 3 is another partition. Okay, and I can have multiple cuts, right? So can cut twice vertically, and then have column 1, column 2, and column 3 being separate partitions, and so on. Okay. So how do we partition the data? Horizontally, vertically, probably both, or none of that. And assuming we have some partitioning, and that partition, as I said, defines the unit of replication. So one partition is what I will be replicating around my system. How do I then decide what to replicate where? Okay, I need to take into account probably performance, because I want to replicate it in a way that makes replication fast, but also makes queries fast, as in queries can easily find what they're looking for. Do I need to take load balancing into account? Probably, right? If I don't, I might end up with a situation where a small number of machines in my cluster end up storing a lot of these partitions. And how about fault tolerance? Definitely, this is something I need to take into account, right? I mean, I wouldn't want all of my partitions and all of the copies of my partitions to end up on just the one machine. I need to make sure that when I copy them around, I take failure domains into account. So remember HDFS, right? So we'll create the first replica somewhere that I can create it quickly, like on the local machine. Second replica on another machine in the same rack. Third replica on another machine on a remote rack, and so on. Okay, and probably there are other considerations here to be made. And finally, suppose that I have my partitioning scheme, so I have my unit of replication, and I have managed to replicate the stuff around. How do I locate the replicas when I need them? Okay, one could say I would have a central mastermind, like with HDFS, right? But we said back then that that was okay for HDFS. Maybe it's not okay in all cases. What can I do then? I could have a distributed directory, right? Where the locations of all of these nodes are somehow also replicated or partitioned and replicated around my cluster. What are the trade-offs here? I will probably gain more fault tolerance, but I might be losing in performance. Maybe. Can I come up with a system that does both, or do I need to? Or how about none of those? Okay, so all of these are things that we need to decide and discuss. So what we will do then now is, I see the time is 12 o'clock here. So let's take a 5-minute break. And in the time we take the break, what I will do is I will assign all of you into breakout rooms. And when we return at 12:05, you should already be in your breakout rooms or enter the breakout room. Then I want you to discuss this in your groups, right? Given the requirements we've seen so far, given the trade-offs we've seen so far, how would you choose to partition your data, like horizontally, vertically, and how would you locate the replica with a mastermind or a directory or something else? And then we will reconvene, and this time I will try and have at least one person from every breakout room report something. Okay, guys? So 5-minute break, and when you return, you should be in breakout rooms. Okay, someone asks, what do you need to discuss in the rooms? I want you to play the role of that designer that needs to decide how should the data be partitioned. horizontally, vertically, or something else? And how would these replicas be created and located? Okay, so answers to these questions here, these three questions. Practically, what I primarily care for is the this first question: how is data partition, and how do you locate a replica? Okay. Okay, so we should be all back here now. So let's go in the order of the rooms this time. So could please someone from room one, just feel free to unmute and tell us what you have.
Hi, can you hear me?
Yes.
Yeah. So for the data partition, we think like it really depends on the query nature. For example, like if a query hits like row more frequently or hits column more frequently, it really like matters our design on the particular storage, like how we store it, right? And for the replica, we think like a distributed system, a distributed directory like HDFS would suit our purpose here, because like if we hit all the queries in mastermind, that probably overloads it, and a distributed distributed system like HDFS naturally solves the problems for us.
Okay, so for the first one, the partitioning scheme, I mean, I hear what you say. So depending on the access patterns, we would pick one or the other. But did you have some like favorite design?
Yeah, that's the problem we're discussing in the breakout room, because we cannot say if one is always superior than the other. So it's really a case dependent thing.
Okay.
Yeah.
Okay, fair enough. And for the second, you said distributed directory, like HDFS. I guess what you mean there is you would store that information on HDFS as opposed to having the same architecture as HDFS, because in HDFS.
Yes. Yeah.
Okay, excellent. Thank you very much. How about room two?
Yeah, so I think ours is more or less similar to that of room one. So we had confusions between for the data partitioning. So it depends more or less on the use case and business requirements. So if it's a transactional data and you're querying a lot of complete records, you have to go for horizontal. Or if it's an analytical and your end product is like a dashboard or a reporting something, then it's easier if you have it as vertical. So since most of the business cases are mostly analytical, so at least that's what I worked on. So I would prefer vertical because it's faster, as well as works more with aggregated queries and everything. But it more or less depends on the use case.
Right. Okay. And how about the second question?
As for the replica, we had actually a division between we are considering both centralized and distributed directory. So like room one said, centralized has less problems with consistency because you're just hitting one particular set of databases. I mean, there's no replica, but it has very less fault tolerance. So I would, I'm not sure what to choose here, because distributed is kind of the way the world is moving towards, but I feel like centralized is better. So I'm not sure.
Okay, fair enough. So to summarize,
Vertical for data partitioning, and not sure for how do you look at a replica.
Okay, good. How about room three?
Hi.
Hello. Hi.
Yeah. So what we were discussing, if some not frequently used fields are there, then definitely we can go for vertical partitioning. We can keep the most frequently used fields in one partition and less frequently used fields in the other partition. And in vertical partitioning, one advantage is that suppose if some fields have needs more security, then in that circumstances we can apply more security control measures into the particular partition. So that is vertical. And horizontal is like if our data is very huge and we need to do a lot of searching and all, in that circumstances, if we are dividing it in horizontally, then when we apply the joining and all, join conditions and all, it would be easy for that case. This is the partitioning. And the second one is I would go for this distributed approach, because centralized having the fault tolerance issue. So we haven't done lots of discussion. So I would prefer this distributed one.
Okay. Okay. Thank you. Thank you very much. Room number 4, right? Number 4. What? Anyone from room number 4? No one from room number 4. If you don't know what room number you were in, room number 4 is Nika, Rachanavi, Robert, Sui, and Zinheng. I think probably butchered the names, but apologies. No one from you? Okay. room number 5 then. Hello.
I wasn't sure if I was in room number 5, but I think it was 6, or maybe
That's
that was
okay.
the participant count. Zoom is confusing. I don't know.
Okay. Okay. Go ahead.
So we didn't have many participants, but for what it's worth, we discussed that we could have data partitioned horizontally. That is namely because it allows for building indices on top of stuff. So this could allow for better, even continuous and rage query access, etc. And also we're discussing key value stores. So maybe based on the key, we would need to get the value that essentially indicates we need to search by keys. We sort of had an idea we agreed on with regards to replicas. We could go for having a similar approach as with HDFS and having locality. So try keep replicas close to clients. However, we also decided that we could keep the replicas active because we don't have a consistency requirement. We could let the replicas also respond to queries and essentially load balance between all replicas. So in a sense, we wouldn't have a main replica and copies, but they would all be servers, right?
Right. Okay.
And this would give a performance improvement and fault tolerance. And with regards to how to locate replicas, we were really unsure. Maybe some hashing on the data, and definitely we were thinking of going in the distributed sort of direction, but we weren't sure about the considerations here. So
right,
that's our contribution.
Okay. Okay. Thank you. Thank you. That was room number 6, by the way. So room number 7, or some room. Anybody who hasn't spoken and is a representative for a room, please feel free to go ahead.
Hello.
Hello.
I'm not sure of my room, but so what we discussed is that the data, actually we didn't reach a conclusion on the data partitioning because each has its own benefits. Like if you vertically split it, right, you can do normalizations.
Okay.
And stuff. So we didn't reach a conclusion there, but about locating the replica, we could go with distributed directories, like basically whatever whatever we have already, like Spark and other stuffs and other distributed architectures, we can use that because as long as the data is eventually consistent, it should be fine.
Okay. Okay. I see what you say. Good. Thank you. Thank you very much.
Thank you.
And I think that leaves maybe one room or two. So anyone else who would like to add something to what has already been reported? No. Okay. Okay. Good.
I think for data
Yeah.
partitioning, I mean, I'm not sure, but we discussed about some kind of hybrid approach where we'll have both horizontal and vertical. Somebody asked a question like, if you have group by kind of query on multiple columns, how you're going to resolve it. So you have an option of, kind of, as you explained, that you have an option of storing for each groups. So something like, tree structure or metadata kind of a structure, which is also in Bigtable, which is also in Bigtable. So because it fits, both the requirements, like where you need horizontally and vertically. So at least on this question, we kind of settled that we need a hybrid approach or both approach to do that. And we were not able to discuss the other one.
Okay. Fair enough. Thank you very much. Anyone else would like to add something? Okay, good. So just to summarize what was said. So for the data partitioning, some rooms decided with horizontal, some rooms decided for vertical. One of the rooms said probably we need something that is in the middle. And I can sympathize with all of you, because indeed the answer is not obvious. So let's go back to those functional requirements and the non-functional requirements we mentioned earlier. Yeah. Remember, the client asked for high throughput reads and writes. So high throughput writes would be fairly tricky to sustain on a column store, on a pure column store. So a pure vertical partitioning would most probably result in reduced write throughput. The client also asked for increased read throughput, but we also know that they will be running analytics on these things. So probably we need a vertical partitioning to support that, right? So it's not clear what we can do, which of the two is the best option. And it seems that we may be able to get sort of the both worlds by some hybrid design. But what would that hybrid design look like? So as your last classmate said, Bigtable has gone with that hybrid. But to be honest, that hybrid is actually a fairly old idea. And it comes, it's no surprise, it comes from the database research community. So I could even point you to the paper that first described that design, where you have you partition your data set horizontally. So you have groups of rows, but then these groups of rows, you store it, contiguous, but in a column major format, right? Bigtable has gone for the opposite of that. So you still do horizontal partitioning. When you store your data, you store it in a row major format, so like a row store, but you partition your data in what they call column families. So you partition it vertically then, and what you have is separate files, separate low-level data stores for each one of those. So you get row store semantics for every column family, but since you can query column families independently of each other, you get column-like access patterns across column families. Okay, so many ways to go about this, and I can definitely sympathize with people who said we are not really sure what's the best option here, because it's not clear. How would you locate a replica? So some of you said, I want a distributed directory because that will give me scalability, would probably also give me fault tolerance and what have you. What's the problem with a distributed directory? The problem is that, the advantages are exactly what you said. A distributed directory would give you probably higher fault tolerance, probably better throughput, and it seems to fit the bigger picture better. The problem is that in a distributed directory, you need multiple hops to find what it is that you're looking for before you get to that thing first. And second, you now have, in a distributed directory, you now probably also have to worry about how you maintain that directory in a consistent state. Okay, so as if maintaining the data store was not a big enough headache, now you need to worry about that for your directory. Only with the directory, the semantics and the guarantees should be more strict, more strong, you know. Okay. For the last question, so how do you locate a replica? That was the distributed version. The central mastermind version has the problem of being a single point of failure, and has the problem of possibly becoming a bottleneck. But it's much faster on the fast path. So if things don't go wrong, the central mastermind is much more efficient, right? We've seen that in HDFS, in Spark, in MapReduce, where you have this central mastermind that keeps track of everything and tries to keep out of the hot path, out of the critical path as much as it can. So how can we achieve like the best of both worlds here? What we could do, for example, is have a mastermind cluster things. So have a small, or I mean, a number of machines, not in the hundreds or the thousands, but a number of machines that store this directory. They only need to coordinate across among them. So you have distribution, but since they are a small number closely tied together, you have this sort of mastermind semantics. You know, just a thought here. Okay, other options are also possible. So this week we were looking into HBase, and we will of course continue next week on HBase. Or actually, let me rephrase that. What we've been discussing so far is fundamentals of distributed NoSQL stores. What we will do in the remaining of this lecture and next week is look into HBase. After that, we will look into Cassandra, and you will see how these things that we're discussing now, they have been addressed differently in HBase or Bigtable HBase or DynamoDB and Cassandra. Okay. All right. So quick detour here, just so to set the pace. Disks are, we know that disks are slow for random IO. They're fast for sequential IO, and sequential IO can be up to 3 orders of magnitude faster, depending on the technology of the disk and the access pattern itself. And this is true for all disks, right? So magnetic, rotational, solid state, like NVMe, you name it. Sequential IO is always much faster than random IO. And this also, to some extent, applies to RAM. Random IO in RAM is slower than sequential IO in RAM. Okay. As a matter of fact, if you have a fast enough disk, sequential disk access can even be faster than random IO in RAM. Okay. So what this means is we need to avoid random IO like the plague when we want high performance. And for now, let's focus on high performance being high throughput. And we'll talk about latency next. Okay. So how can we avoid random IO is the question. Okay. How can we avoid random IO? Let's think about writes. Okay. So you have your clients sending writes requests, like inserting items or updating items, and so on and so forth. How can you avoid random IO in this case, right? So again, think of that mental model of your storage medium being just this long array of locations, and you have addresses there. Okay. So you have inserted some items, Okay, someone says batch processing. Okay, let's think about that, right? So you have already some items in your storage, right? And then a batch or a bunch of operations come in. Okay, let's say these are all writes or insertions. So you look at them. Let's say you take the insertions out and you apply them in a batch and you store them in the end of the end of your array. Good. So we've just avoided doing random IO. But how about the writes? The guys that tell you find that record, the record of student X or the record of client Y, and update their attribute whatever to this new value. Okay, how can we avoid random IO for that? Okay, so that's the kind of challenge we have. And batching is one thing. Appending to the end of a file is the other thing. Okay, so what if we use a log? Okay, and by a log I mean append only storage. So you never override something that is in there. You always go to the end and add new things. Okay. Let me see. So on Slido here, people suggest data clustering based on some keys. That might help, but it wouldn't solve the problem of I want to update that old record I had inserted some time ago, right? Appending to the end of a sorted file, that might help if we have just insertions, but if it's a sorted file, then how do you maintain the ordering? You might have to insert stuff in the middle of something else. So appending, I'll just give the appending to the end of a file for that option. So that would work very well with insertions, as we just said. But how about updates? Okay. Someone says micro-partitioning. You might have something in there, but I'm not sure exactly what you mean. But okay, I mean, let's hold the that line for now, and let's say that the answer is I will use a log. And in the log, I'll just go and append stuff in the end. So how can I make this work with updates? If I always append in the end, how can I update something that I entered some time ago and somewhere in the log, and not, of course, in the end? Okay, people say instead of updating, we can override. If we override, we need to do random IO. We need to search the log, search this file, find where the old item is, and then override it. So that's exactly what we don't want to do. We don't want to have to do this random IO. We will always add stuff to the end. Okay. And the trick here is that, exactly, versions. The trick here is that if I want to update something that is already stored, I will write a new version of that thing at the end of the log. So again, I'm changing random IO to sequential IO, and I always append. Okay. Exactly. You never delete. You never do in-place updates. You just append a new version of whatever at the end of the file. Okay. But what happens with reads now, right? So we've solved the problem for writes and insertions, but what about reads? Now, with this version thing, reads need to scan through the whole storage, potentially through the whole storage, to find what they need. Okay, so let's say I have a record that is, there is a person that has a name, an address, an age, whatever, and I've inserted that thing in my storage. Now I want to go and update the person's age because a year has passed. It's a bad design. I should have stored the date of birth. But let's say I was silly the first time around and I have the person's age in there. So what I would do instead is I would go to the end of my storage and either insert something that says that person's, the key of that person and the new age, or would have a complete copy of that person's record with the new age. Okay. In the first instance, I would have to go to the end of the log and scan towards the beginning until I find the latest version of what I'm looking for. That was for the second case where I have complete copies of the records. If I only store deltas, if I only store what changed in that record, I will still have to go all the way back. I mean, start from the end of the log and go towards the beginning and reconstruct the record as I go, only maintaining the latest version of every attribute of the record. That's a disaster, So that's, I mean, how is that a good idea? Okay, I've made writes fast, but now reads are the worst. What do I do? How do I solve this? Someone says reads based on index. Yes, although in this case, I would have to probably have a very large index. I would have to index every single thing I have in my store. And what happens with these indices is that they're typically of the same order of magnitude as the data that I've stored. Okay, so that's not always a good idea. Someone says read the whole column for all data and get the last entry. Yeah, I mean, that's pretty much what we discussed now. How do you find the last entry? You need to scan through this thing from end to beginning until you find it, and that's not what we want to do. We don't want this. We want to be able to have either the row store semantics. You go to some place, you read a contiguous amount of data, and that's your record. Or if we have a column store, you go to a specific place and you know that that's the last version of the data you're looking for. And that's what we want. But we broke it by doing the trick for the insertions. So how do we do this? How do you find something in a log, right? Let's see. Ideas. I mean, we've been thrown ideas left and right. So micro partitioning, very small partitions, and this means sufficient DML. Ooh. Let me see. So micro partitioning would help in the sense that you would have to do the trick. So what your classmate here suggests, I think, is that let's say you have horizontal or vertical partitioning. Whatever you do, you have more fine-grained internal partitioning where every partition is split into smaller pieces. And so you do the log trick within these micro partitions. So you have less data to do this for. Okay, I think that's the suggestion there. Okay, that can work, and it is a step in the right direction. So doing the log trick, not for my whole table or my whole data, but for the partition we decided to have earlier, like the horizontal or vertical or the hybrid partition. That's a step in the right direction. Timestamps would help, but again, timestamps would help me find what is the latest version. I mean, if I scan through my log and then look at timestamps would allow me to decide that this is a version that's newer than the other version or something like that. But it wouldn't help me locate all of those things, and I would still need to do the big scan. Checkpoints similarly, but what do you mean by checkpoints? So one of your classmates said checkpoints. We may get back to that in a minute. So let's see, I mean, what could we do here? We could say we take the log, we sort it by key, and then we use binary search. Yes, but sorting the log requires random accesses for reads and writes. There needs to be some mechanism, some stage where I say, okay, this is my log. I now need to sort it, right? Because if I do that online, if I do that when I insert things, I no longer have a proper log. What if we split the log into partitions by hash of key, and then we only search relevant partitions? Probably close to what your friend, your classmate there meant with micro partition. and someone says having multiple versions of micropartitions for read. That can all work. What's the problem? If you will have multiple versions of the micropartitions, the space might explode. Okay, the space requirement might explode. It's not a bad idea, but we need to somehow fix the space thing. Okay, chronological order of data, yes. So the fact that we always append in the end implies that these things are, if you scan through your log, you scan it from oldest to newest. So it's already in chronological order, but you need to find the latest version of something. So you go oldest to newest, but you still need to scan that thing, right? Not compress and store data in micropartitions. Okay, so I'm not sure what you mean by compress here. Let's keep that idea of a micropartition, because I said that's a step in the right direction. Okay, we could use a tree-like structure at the storage level, like a B+3 or an ISAM or something like that. Yes, the problem with this is that there is a level of random IO here, and that's what we're trying to avoid. Right? Using an external index, well, we said yes, that could probably solve the problem with reads. Still, would need to go through. I mean, we need to maintain that external index. That would add space. That would add time and complexity. That would add a bunch of things. And probably my write throughput would be going down the drain. Okay. So, every if we need sorting or some predefined structure, then that write throughput that we have, so we fought to achieve by using the log, is lost. Okay. If we have an external index, that's not bad necessarily, but it has scalability limitations. The index adds space, the index adds maintenance complexity, and so that's not the way to go. And this is where this otherwise simple but quite useful data structure, concept comes to play. Okay, the log structured merge tree. So what is a log structured merge tree? It's pretty much what it says on the box. It's a data structure that is structured like a log, but on which you do periodically merges. Okay, so writes and insertions to the log, you batch them or don't batch them, it doesn't matter. What you do is you first apply these things in memory. So you create this batch. And whenever you have a batch of updates, you store them as a separate file. We call them spills sometimes. So there's no single big index structure. We have these log semantics. You always append to the end. If you have an update, you'll just append a new version to the end of the log. And the way this is structured is that these updates, they are batched. Whenever you reach a certain size or certain number of updates, you take those updates and you store them as a file, right? So you have a bunch of these smaller files with updates in chronological order. Each of these are sorted before they're stored on disk. Okay, so you accumulate these updates in this buffer in memory. Before you store it on disk, you would go and sort it by, let's say, key, or by key and column name, or by key and column name and timestamp, or something like that. Okay, so you sort them. This sorting happens in RAM, and you only sort the batch, so it happens really quickly. And then you store this sorted batch on the disk. Okay, once something is stored on disk, you never touch it. It's immutable. Okay, so that little file, the spill, is immutable. No one will go and update something in it. You can only read it. Okay, how do we do updates? Well, these updates go into new files. Okay, just as we said, you append something to the end of this conceptual log, or in essence, you add something to the new batch. When that batch fills up, you sort it, you store it on disk in a spill file, and now you've done your update. So your write throughput is still high. But what happens with reads? There is a question here of how do we sort operations and our operations in spill files so the resulting data. I'm not sure what you mean. If you can rephrase that question or post it on Moodle, I'll address it. So reads now, they will need to inspect all of these spill files. Not good, as we said, right? So how can we solve it? Well, we do a merge. That's the merge part of the name. So every now and then, there is a process running in the background that would go through all of these spill files and would merge them. So, remember, these are already sorted. So merging means that I can go through these files 2 at a time, or more than 2 at a time, and merge together those updates to the correct versions. Okay. How about deletes? Well, because I can still remember, I don't want to go in place and do a delete. A delete in this case is just an update. So I use something we call a tombstone record. So if I want to delete a record, if I want to delete a row, I will go to the end of my log and I will add a new record that says that old record is now deleted. Okay. And eventually, when the merge happens, okay, the merge will see that that version is deleted. So when the 2 files are merged, the deleted version will not be copied to the output of the merge file. Okay. So with tombstone records, every time we delete something, the data size increases, which is counterintuitive. It is a necessary evil, but by periodically merging the spill files, the size will go down eventually. Okay. So we still may need to go through many spill files in this case. How do we decide the time of periodic merge? It could be time-based. It could be based on how many spill files I have. Several ways to decide this. Someone asks, how are reads more efficient here? We're still not there, right? So what we have is very fast writes. We are trying to make reads better as we go. So we periodically merge stuff. So that means if I scan through my data, I will only find something in one place. I won't need to reconstruct that record as I go, with different versions of different attributes and so on. And I can do deletes very quickly again, and with merging, the size will go down. It won't just increase. But reads are still not good here, right? They're still not really good. What I really want is, I have all of these spill files. I want 2 things. One is a way to tell me which of these spill files I should look at, so I don't have to go through all of them. And if I have something that will bring that down to just a few spill files, I need to have a way of saying, of deciding whether what I'm looking for is in one of these spill files without actually scanning them. Okay, these 2 problems I need to still solve. Okay, I need to solve how do I identify a set of spill files I need to read, and for this set of spill files, how do I decide whether what I'm looking for is in each one of these spill files without actually looking at those spill files. And remember, I don't want to have a proper index, because the proper index would add size and complexity. So we will stop here for now. A cliffhanger, yes, just like any good TV series. So we'll stop here and we'll continue next time to see how can we make this work. How can we make reads be faster than what this abysmal situation looks like. Okay. If you have any questions or suggestions or whatever, feel free to post them on Moodle. And otherwise, have a good rest of the week and a weekend, and see you next Wednesday. All right. Good. Thank you, everybody.
Thank you, Professor.
Thank you, Professor.